So this week we'll finish chapter 2. Okay, so this is the last section for chapter 2, which is 2.6, jointly distributed random variables. Thursday this week we'll do practice sessions, and I will assign the first homework for us, okay, which covers chapter number 1 and 2. Okay. Right. So last week we discussed what is probability density function and probability mass function, okay, and also cumulative distribution functions, and how to calculate the mean and the variance for random variables. Okay, so this section 2.6 is called jointly distributed random variables, which means we have two or more random variables. Okay, so in the beginning you may feel like it's kind of very complicated, but allow some time, you will get used to it. Okay, so let's look at this. X and Y are jointly distributed random variables. Okay, and it has joint probability mass function. Okay, probability mass function is for discrete variables. Okay, when it has two variables, X and Y, then the joint PMF, okay, will be like this: Pxy equal to Px equal to X, and Y equal to Y. Okay, and for density function for continuous variables, we have similar things, which is called joint probability density function, okay, which we'll discuss in a moment. And joint probability mass function has the property that when we add all the probability together, Pxy for all the possible X and Y, it will always equal to 100%. Okay, this is always true for mass function and density function. Okay, remember that. Right. So this is an example of jointly distributed random variables. Okay. For X, we have possible values of 129, 130, and 131. And for Y, we have 15 and 16. Okay, and values here shows us for example, X equal to 129, Y equal to 15, the probability is 0.12 or 12%. Okay, and so on. You could also notice we have something here in the last column like Pxx, and in the last row which is Pyy. Okay, that two value is called marginal probability mass function. Okay, which means we add all the possible value of X or Y together. For example, Pxx here equal to 0.2 means, okay, when X is equal to 129, we add the probability for all the possible Y. Okay, all the possible Y is 15 and 16. So basically, for Px equal to 129, this is probability for Y equal to 15 and Y equal to 16 added together. So 0.2 is equal to 0.12 plus 0.08. Okay, so let's see the definition. The marginal probability mass function of X and Y, okay, can be obtained from the joint probability mass function as follows. Okay, so Pxx equal to Px when X equal to small x. Okay, so when the value of X is fixed, we add all the possible Y value. So that is Pxx. Okay, and similarly for Pyy, okay, when Y equal to the small y, when Y is fixed, we add the probability of all the possible x together. Okay, so where the sum are taken over all the possible value of X and Y respectively. Okay. Again,
I'm sorry, but I didn't understand that table that much that you were just showing us.
let me discuss it again. Go back to that table.
Okay.
Hold on. Let me meet more people here. So if possible, could you just join the class, before we start, like 2:30. So otherwise, it's just kind of disturbing to me. Sorry about that. Okay. So in the future,
Yeah.
here, right. Go back to this table. All right. So let's look at here. Pxx equal to 0.20. Did you see that? Okay.
Yeah.
What does that mean? So that means when the x value is equal to 129, right? So when x equal to 129, for y we could have 15 and 16, right? So pxx when x equal to 129 means the x value is fixed at 129, and then we add all other y together. Okay, 0.12 here and 0.08 here. Right. Another example here. Let's look at here. Pyy equal to 0.6. Here, did you see that? This one?
Yeah.
Yeah. For this one, it means when y is fixed at 15, and then we add all the possible x together. For example, y equal to 15, x equal to 129. This is 0.12. Okay, plus when x equal to 130 and y again equal to 15, plus x equal to 131 and y again equal to 15. This is 0.06. So 0.6 here is the sum of all the y together, px, y, when x is fixed as sum for all, when y is fixed at 15, and we sum all the x together. So 0.60 equal to 0.12 plus 0.42 plus 0.06. Okay, and this is defined here, and we call that marginal property mass function.
Okay.
Okay. And this is for discrete variables. And for continuous variables, we have similar things, but we do integration instead, right? So x and y are jointly continuous random variables with property density function of x, f, x, y. Okay, and we have a range for x and y, a, b, c, d, and this is joint continuous random variables. Okay, the property for x between a and b and y between c and d is equal to, when we integration of x, f, x, y for dy and then for dx. Okay, and also for all the density and mass function, all the property added together or integrated together is equal to 100%, as we can see from here. Okay. So this is for continuous variables. And for continuous variables, we also have marginal distribution of x and y. Okay. So if x and y are jointly continuous with density function of f, x, y, okay, and then we can use the following two equations to calculate the marginal property density function. Okay, look at the first one. So f x x, okay, which means for x equal to certain value, okay, we integrate over y for that certain x. Okay, and next one is when y is fixed at a certain value, we integrate for all the possible x. Okay, so this is the same idea as a mass function, but we do the integration.
That looks like a differential. Is that like a differential or partial derivative function?
Yeah, we do the integration of that. Then we need to treat either x or y as constant. I'm gonna show you an example to how to do that. Okay, as you can see here. So for this example, assume that for a certain type of washer, okay, both the thickness and the diameter of the hole vary from item to item. Okay, and x is the thickness in millimeter, and y is diameter of the hole in millimeter also. Okay. So for a random chosen washer, assume that the joint property density function of x and y is here. All right. Okay. Which is when the x between 1 and 2 and the y between 4 and 5, the density function is this. Outside that range, the property is 0. Okay. So the question is asking, first of all, what is probability that a random chosen washer has thickness between 1 and 1.5 and diameter between 4.5 and 5? Okay, so let's do that together. Okay, so based on the density function, okay, the density function looks something like this, and between the range of x is 1 to 2 and y is between 4 to 4.5. So the probability, the diameter and the thickness actually fell within that red rectangular. Okay, so the first part is find the probability, the thickness is between 1 and 1.5 and diameter between 4.5 and 5, okay, which is this pink area. Okay, so we calculate these areas which will give us the probability. Okay, all right, so let's do that together. All right, before we do that, let me share my iPad with you so I can write. All right, okay, this is my iPad notes. Okay, so this is the question. So the first part is asking the probability between 1 and 1.5 for thickness and diameter between 4.5 to 5. Okay, so let's get the first one. All right. Part A, we want to find out the probability for x between 1 and 1.5, for y between 4.5 and 5. Okay, based on the density function, we do the integration. Okay, double integration actually. So the density function is this. dy dx. Okay, so for dy, the range is between 4.5 to 5. And for x is between 1 to 1.5. All right, okay, let's do that together. Okay, so first let's do dy. Okay, so when we do dy, okay, okay, So for y, that is between 4.5 to 5. Okay, so we treat x as a constant and we do the integration for y. Okay, so y, the range is between 4.5 to 5. Okay, and then dx. All right. So that is equal to, okay, let's do it here. So we plug y equal to 5. Okay. It's 25 minus we plug in y equal to 4.5. Square, right? Okay. So this part, then we're gonna do the integration for x again. Okay, so don't forget this dx. All right. And this will simplify as this. Dx. Okay, so let's continue to do integration for x. Okay, so that will become so between 1 and 1.5. Okay, and so on. All right, so the final answer for this part is 25%. Okay. Okay, and you can see from here, which, you know, again, the probability is the pink area, which is 25% of the whole rectangular. Okay, so as we can calculate from here. So 0.24, 25% chance within that range. For the second part, find the marginal probability density function of the thickness x as overture. Okay, so for the marginal function, a second, okay, fxx so we should do the integration of this density function. So density function is this. Okay. For all the possible y. Okay. So
I'm sorry, what's inside of your parentheses again? It's x plus what?
x plus y. This is the density function.
Oh, okay. Okay. All right.
This
Okay.
is, okay. This is one. X plus y.
X plus y dy. Okay.
Okay. So we should do integration for all the possible y. Okay. The range for y is between 4 and 5. Okay. So that's why we do the integration between 4 and 5. So this will become y squared between 4 and 5. Okay, so then you plug 5 into y. Okay, you treat x as a constant. So let me do that. You treat x as a constant and y equal to 5 here. So x times 5 plus 12, y equal to 5, that's 25. Okay. Minus, when you plug y equal to 4 here, x is still x. Okay, so 12 over 16 square of 4. Okay, so that simplified further will become 3 over 4. Okay, so this is marginal function fx x. Okay, so the range for x is between 1 and 2. Okay, because that's the range for x. Okay, outside the range of 1, 2, it will become 0. Okay, we should also write it will be 0, otherwise. Okay, so that is the marginal property function of the thickness x. Okay, the third part is similarly, but we need to find out the marginal density function for y, the diameter. Okay, so which is f y 1. Okay, so if that's the case, again we do the integration for the density function f x y. Okay, but for all the possible x. Okay, so integrate for all possible x. Okay, so this will become, so density function is the same. Okay. For all the possible x, the range for x is between 1 and 2. Okay, so between 1 and 2. Okay. So this will become for all possible x between 1 and 2. Okay, so we treat y as constant. Okay, we plug x equal to 2 here. So this 2 square 12 plus y is still y, x equal to 2 over 6. Okay, so minus, we plug in x equal to 1. Okay, so 1 square 12 plus y is still here, x equal to 1, so that's 6 over 1. Okay, so further simplify, it will become this. Okay, so don't forget the range. This is for y. Okay, for y between 4 and 5. And we also should write 0 otherwise. Okay. All right. So this is the marginal function. Okay. Any questions for this problem and how to do the integration? Okay. So for
I have a question.
yeah, sure.
So like when we do the integration, like you know how there's double integrals, does it matter which way we do it?
It doesn't really
dy
matter. You
dx
can
way,
do
like
no. You can do that either way, but make sure the range is you do not confuse with the range. So you can either first integrate dx and then y, or y first and then x. Doesn't change the final result. Okay, but just be careful about the range for x and y. Okay.
okay, thank you.
Yeah. For marginal function f(x)(x), okay, so we integrate for all the possible y. Okay, and for f(y)(y), we should integrate for all the possible x instead. Okay. Yeah, I know it's kind of confusing and complicated. At the beginning, just keep reading. Let's work together. All right. Oh, one more thing I should say is, for this section 2.6 is pretty complicated because we have two variables, we have this marginal function, and we also have a conditional function, which you will see in a moment. I do not expect to see many of these kind of problems in the exams, but at least you should follow the examples I discussed here. Why we should integrate for x or y for what range. Okay, you should follow the procedure at least. Okay, and we could have more than two random variables. Okay, just show you the general format of the equation here. If we have more than two joint discrete variables, xy, x2, xn, okay, and the joint property mass function is this. Okay. And if the variables are jointly continuous, and then the joint property density function will be this. And to calculate the probability, we could either do the sum or we do the integration multiple times, depending on how many n's we have, the number of variables we have. Okay, that's the general format of the equation. Okay. Here is the means of function of random variables. Okay. So if x are random variables, and if the function is this h x, okay, and then if x is discrete variables with PMF of px, okay, then the mean value of the function of x, okay, is given by this equation. Okay. And the sum again is taking over all the possible value of x. Okay. And if x is a continuous variables, and then we should do the density function. Okay. We use this set of this equation. Right. Okay. And for comparison, I also write down the mean value for x. So for discrete variables, the mean value will be x times px. Okay, so compare these two equations. You see we have hx here, and we have x here. For continuous variables, mu x will be this. Okay, so this is what we discussed last week. This is x fx dx. Okay, so you can compare these two equations. Okay. Okay. Again, if you have more than two variables, x and y, jointly distributed random variables, and each xy is a function of xy. Okay, and then we should do the multiple integration or multiple sum. Okay. Okay. And then let's look at another example here. So internal combustion engine has several cylinders bored into an engine block. X is the bore diameter of cylinder in millimeters. Assume the property distribution function of x is this. Okay, so fx is equal to 10 when x between 80.5 and 80.6. Outside that it is 0. Okay, so when the diameter is between 80.5 and 80.6, the probability is 10. Okay, and A is the areas of the bore, okay, which is the function of the diameter. Okay, so A is a function of x. Right. The question is asking the mean value of the area. Okay. So based on the equation we just learned, okay, so for the mean value of a function, the mean value of hx fx dx. Okay, and here in these questions, the function is a, okay, which is equal to pi x square over 4. Okay, so here hx is equal to a. So then use this equation. So hx fx dx. Okay, and fx is 10. Times 10 dx. Okay, and then we can just do the calculation. The mean value turned out to be so 5096 square millimeter mean value. Okay, question about this example? Yeah.
A is not necessarily representing the area in this.
A represents the areas of the bore. Okay.
A does represent the area of the bore.
Yeah,
Okay.
it does. Yeah, I can see it here. Okay. Yeah, and because a is a function of x, okay, so we can use this equation to find the mean value of the function of x. Okay. You know, basically, the mean value of areas is equal to this. Okay. Right.
And then I'm looking at your h of x definition equals the area equals 4x squared over x.
Oh, sorry, it's a pi. Or pi squared, yeah.
It's supposed to be pi. Oh, okay.
Pi. Sorry.
I was kind of wondering how you figured that out. Okay.
Okay, thank you. So this is a marginal function. Any more questions?
Yeah, I'm just looking at your notation. So you go from the integral of negative infinity to positive infinity pi x squared over 4 fx dx, and then it goes to x. Is
Yeah.
that an x or is that a multiplication symbol?
Times. You
That's
mean it's times 10.
times. Yeah, that's times.
Yeah, fx is 10. So I simplify the procedure a little bit. Okay.
That's the piecewise. The piecewise up there. Okay.
Yeah. So I simplified the procedure, to save some time, but to write it down, it should be this. Okay, 10 dx. So the range is between 80.5 to 80.6. Okay, and then you plug 80.6 into x minus you plug 2.5 pi. Okay, become okay. It will become this. All right.
Thank you for that.
And then we have some more information. Okay, conditional distribution. Okay, we just learned what is marginal function. Okay, and conditional distribution. Let's look at what does that mean. If x and y are jointly discrete random variables, okay, with joint property density function of pxy, okay, and pxx is the marginal mass function, okay, and x is any number for pxx larger than 0. Okay. Then the conditional property mass function of y given x equal to x is equal to this. Okay, so py, the straight line here, means given x is equal to certain value of x. Okay, so that is equal to pxy over pxx. Okay, that's right. So the bottom part is the marginal function. Okay, as x meets the here. So this is the marginal mass function of x. This part. Okay, and top part is the joint probability density function, pxy. The joint function. Okay, and the ratio of these two is the conditional probability mass function. Okay, so that's the probability for y given x is equal to a certain value. Okay, so the value of x is fixed. For continuous distribution, similarly, but we do the integration. Okay, so x, y are joint continuous random variables. Okay, and joint PDF is this. Okay, and fx is the marginal density function of x. Okay, and the conditional probability density function of y given x equal to a certain value of small x. Okay, again, this is given. The probability of y when x is fixed at certain value of x. Okay, it is equal to this. Okay, oh. Again, the bottom part should be fx. So that is the marginal density function. Okay, and top part is the joint probability density function f. xy, this part.
Could you just, I don't know, I'm just a little confused about why we have conditional distributions and then the difference between continuous conditional distributions.
Yeah. So what is conditional probability? We learned what is conditional probability probably last week or 2 weeks ago. So that is under certain circumstances. Okay, and we want to find
Okay.
out the probability of certain things. Okay, in this case, that circumstances is when the value of x is given. Okay. Okay, I'm gonna show you what does that mean in a moment when we go back to the previous example. Okay, and you will have an idea what does
Okay.
this really mean. Okay, physically. Okay, yeah. All right. So just continue. Okay. So this is continuation of a previous example, asking the probability that the hole diameter is less than or equal to 4.8. Given that, okay, so given that it is the condition. Under the condition that the thickness is 1.2 millimeter, ask the probability that the hole diameter is less than or equal to 4.8. Okay. All right. So that's the combination of what we just did. So first of all, let's find out fxx. Okay, so that is the marginal probability density function. Okay, which we get from the previous slides. Let me just write it down. Okay, so that's the marginal PDF. So that is from the previous slides. Slides 131. Okay. But we also need the joint PDF. So for the joint PDF, fxy, so this is given, it's this one. Okay, so the joint PDF is this, and the marginal is this. Okay, then let's figure out what is the conditional. So the conditional PDF for y given x equal to 1.5 millimeter. So the question is asking this. The probability for y is the hole diameter. Okay. Given x is a certain value. That certain value is 1.2. So that is equal to the joint PDF fxy when x equal to 1.2 over the marginal fxx, okay, when x is equal to 1.2. Okay. And for the joint PDF is this part. Okay. So we plug in the joint. 1 over 6 x 1.2 plus y. plus y. Okay, over the marginal function, this part, okay, 1/6 x 1.2 plus 4.5. Okay, so that this part, the bottom part is here, and the top part is this part, joint function. Okay. So this is for y between 4 to 5. Okay. Simplify this, it become 1.2 plus y over 5.7. Okay, so this is for y between 4 and 5. Okay, and it will be 0 otherwise. Okay, then go back to what the question is asked. So the question is asking the probability of y less than or equal to 4.8. Okay, given, the straight line means given x is equal to 1.2. Okay, so y larger than 4.8, less or equal to 4.8. So let's do the integration from negative infinite to 4.8, right? And then we do the integration for conditional PDF, fy given x, okay, which is y given x equal to 1.2 dy. Okay, and that is equal to 4 to 4.8. Okay, because the smallest possible y is 4. Okay, so we do the integration from 4 to 4.8, and then the conditional probability is 1.2 plus y over 5.7 dy. Okay, so this part. Okay, all right. And this is 0.786. Okay. Question for this? All right, let's continue. Conditional expectation is another term for mean. Okay, basically, expectation is another term for mean when considering probability. Okay, and conditional expectation is a mean value or expectation which is calculated using conditional PMF or PDF, depending on it is discrete or continuous variables. Okay, right, and the conditional expectation y given x equal to a certain value x is equal, we can write as this. E is for expectation. Okay, y, the straight line is given. Okay, y given x equal to certain x value. Okay, or you can write as the mean value, mu y given x equal to certain value x. Okay. So find the conditional expectation of y, also from the previous example, given that the thickness is 1.2 millimeter. So expectation of y, sorry, okay. So E expectation for y given x is equal to 1.2. Okay. So that's equal to y for conditional function when x equal to 1.2 dy. Okay. For the range of y, it is 4 to 5. Y. This part, which we just calculate from the 2 slides ago, is 1.2 plus y over 5.7. Okay, dy. All right.
Quick question
Sure.
is I'm just wondering if that's a capital F for a specific reason, or in your first integral.
Here. Oh.
Yeah. Is there a specific reason why you capitalize that F, or?
No, not really. It's just like
Okay.
conditional,
Okay.
conditional function. Okay, from the slides 139. Okay, it is this part. Okay, this
Okay.
actually should be a small f. Small
Okay, I'm just wondering if, or I was almost confused if maybe you're trying to put an E up there and forgot to put the bottom leg. Sorry about that.
No, sorry. Okay, yeah, should be a small f. Okay. All right. All right, let's continue. Any questions?
Could you scroll down just a little bit so we could see the top part of that equation that you were the
Okay, so I
a little
skipped
bit more?
details.
I'm sorry.
Yeah.
Okay, there we go.
Okay. Yeah. So independence
Oh, I
for
thought you.
Hmm?
I'm sorry, that's not a fraction, is it? You just underlining to note that it's from the previous expression?
Yes.
Okay.
And the next slide is talking about independence for two random variables. Okay, and if x, y are independent random variables, okay, and for joint discrete variables, then p x y equal to p x x times p y y. So that is the products of marginal functions. Okay, so marginal functions of x and y. Okay, if x and y are continuous variables, then the joint property density function is equal to the product of the marginal also fx x and fy y. Okay, so of course this is providing x and y are independent. And if I have more than two variables, okay, this equation will hold true, providing x1, x2, and xn are independent. Okay, and these two equations will hold true. Again, this is not L. This will be ... This is not L. This is ... Okay, so the products of the marginal functions, depending is discrete or continuous variables. Okay. And if x and y are independent variables, then the following two equations also holds true. Okay, if it's discrete variables, okay, and if the marginal function larger than 0, then this is conditional PMF of y. Okay, conditional probability mass function of y equal to the marginal function. Okay, so this is again the marginal PMF of y. Okay, again, the condition is they are independent. For continuous, similarly, but it becomes fx, fy given x. So that is the conditional PDF of y equal to the marginal PDF of y. Okay, when x and y are independent. Okay. And then let's go to that old example. Okay, so in this discrete variables, here give the probability of length x and also the thickness, asking are these two variables are independent or not. Okay, so we can calculate pxx and pyy. Okay, and see if they are equal to pxy. Okay, for example, when x is equal to 129, okay, when y is equal to 15, okay, and then pxx, okay, so pxx is equal to 0.2, okay, 0.2, and pyy will equal to 0.6, 0.6, right? And pxx times pyy will equal to 0.2 times 0.6 is equal to 0.12. Okay, so we check if this is equal to px and y. Okay, and pxy is here, 0.12. So yes, in this instant, pxx times pyy is equal to px and y. Okay, and we should also check all the other 5 combinations. For example, x equal to 130, y equal to 15. Okay, okay, and so on. Okay, we check everything, and turned out all of pxx times pyy is equal to pxy. So turned out they actually are independent. Okay. All right. Covariance. So this is a new definition here. So x and y are random variables with different mean values, mu x and mu y. Okay, and covariance is defined as this equation. COV means covariance. Okay, so covariance of xy equal to the mean value of, what do we call this? The mean value of the product of x minus mu x. Mu x is the mean value of x times y minus the mean value of y. Okay, so what covariance measured? Okay, so covariance is measurement of the strength of linear relationship between two variables. In our case, x and y. Okay, so a measurement of strength of linear relationship between x and y. Okay. And we can also calculate the covariance using this equation. So whichever is easier. Okay. So covariance again is a measurement of the linear relationship between two variables. All right. And the next question is pretty complicated, unfortunately. Okay, but let's just do it all together. Okay, so again, I do not expect to see questions similar to this kind of difficulties in the exams, but at least you should try to understand the steps, the procedure, and why we should do that calculation. Okay, and what range of integration we need to do. Okay, so let's read this question together. We may not finish this question by today, yeah, but anyhow, a mobile computer is moving in the region A, bounded by axis, the line x equal to 1 and the line y equal to x, okay, which is here. So the region by this triangle, okay, one line is the x-axis, another line is x equal to 1, which is this line, and the other line is y equal to x, is this line. Okay. So xy denotes the position of the computer at any given time and give us the joint density of x and y. Okay. So we have joint density function fxy equal to 8 xy when the point of xy at A. So when the point is within that triangle, the density function is 8xy. Okay. Outside this triangle, it is 0. So no chance outside A. Okay. So question is asking find the covariance x and y. So covariance we can calculate use either one of these two equations. Okay.
It looks easier to use the bottom alternative
That's what
version
we're
of
gonna
that
use.
equation.
Yeah, that's what we're gonna use. So we use the bottom, the second equation here. So covariance is equal to mu x y minus mu x times mu y. But still is a lot of calculation, and I don't think we can finish by end of the day. So covariance equal to mu x y minus mu x times mu y. All right, and let's find each of these three one by one. Okay, the first one, mu x times y. Okay. For the first one, let's find out this one. Okay. The mean value of x times y. All right, so what we should do is we should do the double integration. Okay. Okay. Because we are going to do the mean value of x and y. Okay, and let's consider x and y is a function of x, y. Okay, so the mean value of a function h x, y based on the previous equation is equal to hxy fxy dx dy. Okay, and here the hxy is x times y. Okay, because we trying to find the mean value of x and y. Okay, and then let's view equal to x and y fxy dy dx. Okay. Then let's pay attention to the range. X and y, fx and y, that's 8xy dy dx. All right, so let's do the dy first, and then do the dx second. Okay. So the range for dy is between 0 and x. 0 and x. Okay. So why is 0 and x? So that is because for certain x, the range of y is between here 0 and here is x, because this line is y equal to x. Okay. So first of all, we assume x is constant. We do all the integration for y, and y, the range is between 0 and x. 0 and x. Okay. So this part will become, that is 8x squared y squared dy dx. Okay. For this part, it will become 8x squared. Okay, we treat x as the variables. Okay, for all the possible y. Between 0 to x. So that is for y value. Okay, and then dx. And for this part, that will become 3, 8. Okay, so when y equal to x, so that become x to the power of 5, right? Minus when y equal to 0, so y equal to 0, this is 0. Okay, minus 0 dx. That will equal to 3 times 6, 8 to the x to the power of 6, right? And between 0 and 1, plug 1 into the x, it will be 8 times 1, 18 minus 0. So that is become 4/9. Okay, so that's mu x and y. Okay, so we resolve this part first, and Thursday let's do the mu x and mu y. Okay, so let's stop here for today.